penalty function method, these are used for solving the general nonlinear programming problem. Now, in penalty function method, what it does, the problem reduces, the nonlinear problem is being reduced to a sequence of unconstrained optimization problems. Thus, let us consider a general nonlinear programming problem in this fashion. Find x. There are n number of decision variables which minimizes the objective function f x, which is nonlinear in nature, subject to, since we are considering a general nonlinear programming problem, that is why let us consider a sequence of linear, that is nonlinear equations with equality constraints. Say there are p number of equality constraints, and let us consider another set, these are inequality types and m number of inequality constraints. Now, penalty function method, what it does, it reduces this nonlinear programming problem into a sequence of unconstrained optimization problem, because thus this penalty function method can also be named as the sequence of unconstrained minimization technique. That is the full form is sequence of unconstrained Now, today I will tell you how we are just handling this sequence of unconstrained minimization problem in penalty function method. There are two types of penalty function method. One is the exterior penalty function method and another one is the interior penalty function method. In exterior penalty function method, a sequence, it generates a sequence of infeasible solutions one after another, and once it reaches to the feasible, this is a iterative process. Now, once it reaches to the feasible space, then the iteration process stops, and that is the exterior penalty function method. But in the interior penalty function method, I will explain you with the example as well as graphically. What it does, it generates a sequence of feasible points, but it will convert to the optimal solution of the original problem. Now, whatever I said, let me just elaborate the things with the mathematical form. Now, as we see for the equality constraint, how the penalty term is coming in the penalty function method, let me tell you that factor first. Now, say this is these are the equality constraints. Now, we are on iterative process is running. If in the process there is a solution, say x1, which is infeasible, then certainly at the point x1, hk x1, at least one of these will not be satisfied, because once it is being satisfied, then only this is the feasible point, otherwise this is infeasible point. Thus, we can say that in the process of iteration, if at some iteration x1 is the guess point of the optimal solution, which is not feasible, in that case hkx not equal to 0, at least one hkx. For at least one k, hkx 1 not equal to 0. Now, from here the penalty term is being formed. It is being said that if x1 is infeasible, then we are incurring one penalty, that is hkx1. Now, since penalty sometimes is positive, sometimes it is negative, that is why the penalty can be said as the square term. Thus, we can say if we just multiply with a parameter mu k, say, then for not being achieved the feasible solution, this penalty we have to incur for equality constraint. Now, let us see what is happening for the inequality constraint. And now, inequality constraints are of the type GJX less than is equal to 0. That is why if again in the same thing, if x1 is a solution, rather the guess point for the optimal solution at any iteration, and if x1 is not feasible, then at least for one j, GJX is greater than 0, because if GJX is less than equal to 0, that means x1 for all j, then x1 must be the feasible point. That is why since x1 is not the feasible point, we can say the GJX is less than 0, and at least for one j, that also should be the logic here. And here we can say that we will incur a penalty, that is the, what is the amount of it? Amount is GJX. That is why we can generalize this with a penalty function max of 0 GJX. It means that if x is within the feasible space, the penalty is 0. If x is outside the feasible space, then we are incurring the penalty value, that is GJX1, alright. And we can even again multiply with a penalty parameter mu j. Now, in the penalty function method, what it does, it converts the constraint problem, constraint nonlinear programming problem into the unconstrained minimization problem in the following fashion: minimization of fx plus mu summation hk square x, that is the penalty for the equality constraint, this is from 1 to p mu k. I should write down mu k here inside the equality sign, plus summation j is equal to 1 to m, because there are m number of inequality constraints. We can write down mu j, let me put it prime, max of 0 GJX. How we are summarizing the nonlinear constraint problem into the unconstrained problem, just you see, we are considering the objective function plus we are attaching, we are appending, we are augmenting the penalty terms. Now, for equality constraint, this is the penalty term for any selection, that is infeasible selection, and for inequality constraint, this is the penalty term for any infeasible selection. Thus, we can say that we are trying to minimize the total penalty as well as we are trying to minimize the function fx. That is why these are all coming into the additive form, and this could be the representative of the given original nonlinear programming problem. That is the basic philosophy of the penalty function method, but let me just detail the interior penalty method and exterior penalty method in specific. Now, there are few functions we are considering for interior and exterior penalty function method. Now, these are the popularly known functions. Let me first consider the interior penalty function method. Now, only the differences are there in selection of the penalty terms. We can consider the penalty terms for the interior penalty function method. The very well known method is the inverse barrier function. In other way, the interior penalty function method is also being named as the barrier method. The function is minus 1 by GJX. This interior penalty function method works only for the less than equality type of constraints. Now, this is inverse barrier function, and as I said, the interior penalty function method is being considered, is being taken, that function is being taken in such a way that in every iteration we will move through the feasible space and we will converge to the optimal solution of the original problem. How the inverse barrier function is being used, I will just tell you in the next. There is another barrier function that is a very popular function, that is a logarithm barrier function is also being considered, that is the term is minus log, that is a natural log base E minus g j x. Why we have considered this kind of functions, I will just in the next I will show you one example. And similarly for the exterior penalty function method, the popularly known functions are, as I just said, max of 0 g j x or max of 0 to the power p, where p is an integer. Now, in the next I will show you how it is being used, both the functions in both the cases. Let me consider one example, simple example. This example is minimize x subject to 5 minus x less than equal to 0. If I just draw it, then certainly, and if this is the x equal to 5, this is the feasible space for us, x greater than equal to 5 is the feasible space, and minimize x means certainly at x equal to 5 the solution is coming. This is a simple problem we have considered. Now, here we are using the interior penalty function method and we are using the exterior penalty function method separately. As I said, in the interior penalty function method, the popularly known function is, let me consider the first one, inverse barrier function. We can consider log function as well. Now, in the interior method, we consider the unconstrained problem, rather converting this problem into the unconstrained problem in this manner, f x plus mu into 1 minus mu into minus 1 by g j x. That means, mu divided by 5 minus x. This is the unconstrained problem for us. Now, if we consider, let me draw the picture how the method is being implemented. Now, this is the iterative process. What it does, if I consider say mu is equal to 100, then the function will come this way, asymptotic function, all right. Now, x minus mu by 5 minus x for mu is equal to 100, this is the function. Certainly, this is the unconstrained problem, apply any unconstrained optimization technique and that we can achieve the minimum at here. Now, let us reduce the value of mu, then the function will come here, say mu is equal to 10, function is coming here, then the minimum is coming here. As and if we just reduce mu further and further in this way, the unconstrained problem only generates a sequence of optimal solutions for different mu, and these optimal, the optimal of the individual unconstrained problem will approach to the optimal solution, all right. That means, thus this means that for a complicated nonlinear programming problem where objective function is very complicated function, even the constraint is very complicated function, we will just convert the optimization problem, the nonlinear problem, into the unconstrained problem, and for different value of mu we will solve a series of unconstrained optimization technique, and that sequence will generate, that sequence of problem will generate another sequence of optimal solution which will approach to the optimal solution of the original problem, where x star is the optimal solution here, all right. This is the interior penalty function method. Thus, we can summarize that the function has been taken in such a way that the functional form here, the inverse barrier function, just now I have just mentioned minus 1 by g j x minus 1 by 5 minus x, and we are considering g j x as lesser than type equal to constraint, and this will automatically move through the feasible region and it is converging to the optimal solution. That is the interior method. Thus, we can summarize, if mu tending to 0, then the optimal will converge to sequence of optimal solution will converge to exter. Now, let us consider the exterior penalty function method. For the same problem, where is the only difference? Difference is only in formation of the unconstrained problem. Now, here the formation would be x plus mu into max of 0 GJX, that means max of 5 minus x. Let me consider square. As I said, p could be any integer, I can consider square, I can consider cube, I can consider even the linear function. Generally, we are avoiding the linear function because since we are solving the unconstrained optimization problems, that is why there is a need to apply the necessary and sufficient conditions as we did for the classical optimization technique. Unless the function is of at least second order, this is second degree, it is very difficult to do the second order derivative. That is why let us consider at least the power of the penalty function as square. We can consider cube, 4, anything. Now, if this is the form of the unconstrained problem for the exterior penalty function method, just see what is happening in this case. This is x equal to 5, all right. Now, this is y is equal to x, sorry, this is y equal to x, all right. And what it does, for large mu, this is the function, this function, and certainly optimal will come here, and for lesser mu, rather I am sorry, for the very small mu, say mu is equal to 0.1, all right. Now, if we move to point mu is equal to say 10, then this is another function, it should be here. We know that here is the optimal. Now, for another mu, the optimal will come here. In this way, it will proceed, say mu is equal to 100. As mu tending to infinity, for this function, this optimal solution, series of sequence of optimal solutions will approach to x equal to 5. That is the beauty of this function, that is a penalty function in exterior penalty function method. That is why the penalty terms have been taken in this fashion. The interior, this function automatically guide us to move through the feasible space, and it will generate a sequence of optimal solution which will approach. For mu tending to 0, it will approach to the optimal solution of the original problem. And for the exterior penalty function method, if we consider this kind of function, automatically it will guide us to move through the infeasible space, because this is the feasible space, through the infeasible space, so that the sequence of optimal solution will approach to the optimal solution of the original problem in this fashion. That is the basic philosophy of the interior and exterior penalty function method. Let me write down the algorithm for both the methods. Step 1, start with an initial phase basic feasible solution, say x1, because we need initial feasible solution, because since we are solving the unconstrained optimization problem, any technique we have learned that can be applied here, but for some methodology we need the initial solution, and which will be updated in the respective, in the other iterations. and so that the functional objective functional value will decrease further for minimization problem. That is why initial solution selection is very important for this penalty function method. And for the interior penalty function, we are considering the initial solution as a feasible point, and for the exterior penalty function method, we are considering the starting point as an infeasible point, because from infeasible space we are moving to the feasible space. Now, start with an initial feasible solution x1 such that for all j, gj x1 is lesser than 0, then only x1 is the feasible solution. Now, let us select some mu 1, because as I said, since mu 1 is approaching to 0, that is why mu 1 could be very high value initially, and select mu 1 and solve unconstrained optimization problem as I have just explained by augmenting either the inverse barrier function or logarithm barrier function. Once we are solving the unconstrained minimization problem, then we will get the next solution optimal as x2 say. Now, since this is the iterative process, let me set k is equal to 1 here, so that in the next we can move to k is equal to 2. All right. And mu 1, that is the mu k, will be updated with a new value mu k plus 1, that is lesser than mu k. Generally, we are considering mu k plus 1 is equal to c into mu k, where c is lesser than 0, lesser than 1, because we wanted to reduce the value of mu than mu k. That is why we are selecting mu k plus 1 is equal to c into mu k. Again, we are solving the unconstrained optimization problem, minimum problem with the augmented penalty term certainly, and we will get another optimal solution x3. In this we will repeat the process, and unless we will just do the iterations one after another, unless the series of optimal solutions will converge to a point. Thus, it is being said that the sequence of optimal solutions, whatever we are achieving through the interior penalty function methods, the limiting point, the limit point of that sequence is the optimal solution of the original problem. Now, let us consider one nonlinear programming problem in the next, and we will solve it. Let us consider a general nonlinear programming problem where the objective function is x1 minus 2 x2 subject to the constraint 1 plus x1 minus x2 square greater than equal to 0 and x2 greater than equal to 0. As I have discussed, all the constraints are of the type less than type. Let us convert these both inequality constraints to the less than type. That is why it would be now we are applying the interior penalty function method. Let me consider the logarithm barrier function here. That is why the unconstrained problem could be minimization of x1 minus 2 x2 minus mu log of minus gj x 1 minus mu log of minus gj x 2. This is the unconstrained problem. Let me name this function as phi. This is the function of x1, x2 and mu. Now, we have to solve this by supplying the value for mu, different value for mu. We will start from a high mu value and we will approach to mu tending to 0. But before to that, let me solve this one with the classical optimization technique. Then the necessary condition would be this equal to 0 which will give me 1 minus mu divided by 1 plus x 1 minus x 2 square equal to 0. And the second condition is that minus 2 plus 2 mu 1 minus x 1 minus x 2 square minus mu by x 2 equal to 0. These are the necessary conditions. We have to get the values for x 1 x 2 which will satisfy both the equations, that would be the stationary points. From there we have to select that point of x 1 x 2 which will minimize the function f x. That is the idea of the unconstrained technique. That is why from here, from the first equation we are getting that 1 plus x 1 minus x 2 square is equal to mu. If we just substitute this value here, then here 1 would be there, 1 x 2 will be there, because 2 mu x 2. Then we are getting one equation as x 2 square minus x 2 minus mu by 2 equal to 0. And from here we are getting the value of x 2 as 1 plus minus 1 by, alright. Now, from here only the plus is the feasible solution, that is why we will not consider minus at all. If we consider plus value for x 2, then we are getting x 2 is equal to 1 plus root 1 plus 2 mu by 2, and if we substitute this value in the other equation, then we will get x 1 is equal to root over 1 plus 2 mu plus 3 mu minus 1 divided by 2. Alright. These are the stationary points for us. Now, how to get the optimal solution for the original problem? The technique we have just learned, we will consider f mean, that is the f is a objective function of the original problem. This would be mu tending to 0 phi x 1 x 2 mu. Similarly, we will get x 1 star is equal to, that is the optimal solution of the original problem, as limit mu tending to 0, this value 1 plus 2 mu plus 3 mu minus 1 divided by 2, and this value will give us the value for x 1 as 0, alright, and x 2 star would be limit mu tending to 0 1 plus, and this value is 1, alright. Once we are getting that, then we are getting the solution of the original problem as x 1 star is equal to 0, x 1 is equal to 1, and the minimum value for f would be then minus 2. That is through the classical optimization technique by considering the interior penalty function method, and with the idea that mu tending to 0 in the interior function we are getting the solution. Same thing if we just apply the iterative process for different value of mu. If we start mu is equal to 10, for different value of mu, just see how the values are being progressed from, for 10 this is x 1 star, x 2 star, and this is the original f, and this is phi, this is not f, this is phi, alright. Similarly, mu is equal to 1, these are the values, and once mu is approaching to 0, that means we are reducing the value of mu further and further. Just you see x 1 is approaching to 0, and as we have seen the original x 1 star is equal to 0 and x 2 star is equal to 1, we are approaching to that value, just you see, and the original f mean we are approaching to minus 2. That is the beauty of this method. The method tells you that instead of applying the classical technique that way, we can solve the unconstrained optimization problem as every iterations, and we will just approach to the optimal solution. That is the proof, just I am showing you. And since this is so, from here we can develop a result, and entire interior penalty function method is based on this result. If the function f x minus mu summation 1 by g j x j is equal to 1 to m, if we are having m number of inequality constraints and minus 1 by g j x is the augmented penalty term, then if we consider mu for all constraints, we can consider different mu's even, but for simplicity we are considering single mu. This is minimized for a decreasing sequence of mu's and the unconstrained minima for every mu, if we consider the iteration as k starting from 1, then for every k we are getting one optimal unconstrained minima converges to the optimal solution of the original problem. As mu tending to 0. Thus, we can say that if x k stars, this is a sequence of optimal solution for unconstrained problem, then the limit point of this sequence is the optimal solution of the original problem. But one thing is that there is a disadvantage of this method even, because if we consider once the x is lying on the boundary of the feasible region, we could see that this augmented penalty term will go to infinity value, because z j x would be is equal to 0, but we will get this value as infinity. That is why that is the only disadvantage of this method, but with the extrapolation technique I will just mention at the end, and with the extrapolation technique we can remove this disadvantage. Now, similarly we can explain the exterior penalty function method. Let me write down the algorithm. Step 1, start with an infeasible point, because this is the reverse to the interior method. Consider a suitable mu 1 as well and solve unconstrained equivalent unconstrained problem, then we will get x 2. What is that problem? The problem is f x plus mu summation max of g j x to the power p for different value of mu, we will solve this unconstrained optimization problem. First we will start for a suitable mu, and mu should be starting mu should be very small value, because we are approaching to the high value. Mu with tending to infinity, we will get the solution. Then the step 2 would be get optimal of this problem. If this is x 2 star, then we will test whether x 2 star is feasible or not. How to check? We will just consider whether g j x 2 star is less than equal to 0 or not. For all j, we will just check. If we see that x 2 star is feasible, then we will stop our process. If it is not, then we will go to step 3. How we will go to step 3? If I just start with k is equal to 1, the iteration 1, then we will update k to k plus 1, and what else? We will consider in the next mu k plus 1 is equal to c into mu k, because we are approaching to the high value, that is why c must be greater than 1. All right. As we have seen for the interior method, it was less than 1, but here it would be greater than 1. Then we will get another unconstrained problem. Say this is mu k, we will get another unconstrained problem, and we will solve it. We will get the optimal, we will check whether this is feasible. Once it is coming feasible, we will stop our iteration. That is the idea. And otherwise, we will just run the methodology, and we will reach to the optimal solution at the end. Series of sequence of k stars again we will generate, and the limit point of this sequence as mu k tending to infinity, that would be the solution for the original problem. Let us consider another example for this to explain this methodology. Minimize f x. Here we are considering nonlinear objective function. We can consider the nonlinear constraint as well, but we are considering the linear constraint of less than equality type. To illustrate the methodology, let us consider the unconstrained problem, that would be objective function plus mu max of 0, and we are considering square because we wanted to apply the classical technique for getting the optimal solution for the original problem. That is why this is a unconstrained problem, we wanted to minimize this. This is phi. All right. If this is so, then again the same, del phi by del x 1 equal to 0, del phi by del x 2 equal to 0. From here, if we just apply, we are getting from the first equation x 2 plus mu to mu x 1 plus 2 x 2 minus 4 equal to 0. This is for infeasible points, and for the feasible points we are getting this value as 0. That is why this term will not contribute anything here, only minus x 2 equal to 0. That is why the only solution x 1 equal to 0, x 2 equal to 0. But here if we consider only the infeasible points where the penalty term will give some positive value, then we are getting minus x 1 plus here it is 4 mu x 1 plus 2 x 2 minus 4 equal to 0. Now, from both the equations we are getting x 1 star is equal to 2 by 1 by and x 2 star is equal to 1 by, and once mu is tending to infinity, this x 1 star value will approach to 2 and x 2 star value will approach to 1, and this is the optimal solution of the original problem. Now, here also we can generate we can apply the iterative process instead of applying this classical technique. For several mu, we will generate a series of values of x 1 star and x 2 star. We will see that for mu tending to infinity, that series will converge to these values. But that is all about the interior and exterior penalty function method, but there are few things to be discussed here. One thing is that, as you have seen that for both the methods, if we select mu in such a way that we are getting the optimal solution at the boundary of the feasible region, then the process fails. This is one thing. That is why there is a method that is called the extrapolation technique, through which very nicely we can guess the true minima of the original problem. That extrapolation technique is how to do that, as we are getting a series of mu k's and series of x k stars, all right. Then what we can do, we can formulate a function to obtain the minima of the original problem as a function of mu, that is of power, say anything of our own choice, mu square. Say let us consider rth degree polynomial mu to the power r, all right. And once we are supplying the value of mu, we will get 1 x star, because we are doing the interpolation now. Then for let us consider, instead of going the rth order polynomial, let me consider a single first order polynomial here. Then very nicely just see where we are reaching. Say we are considering x star mu as a0 plus a1 mu. That means we are interpolating a linear line. We are having a series of mu k's, we are having the series of x k stars, and from there we are trying to interpolate a linear line. Then if we just we will get k number of equations with k number of unknowns, and from here we can find out the value for a0 as x k star minus mu x k minus 1 star divided by 1 minus mu, and a1 we are getting as x k minus 1 star minus x k star divided by mu k minus 1 minus c. These are all c. How we are reaching that, let me just tell you. Say we are having 2 points, x k stars and x k plus x k minus 1 star. So that we are getting x k minus 1 star is equal to a0 plus mu k minus 1 a1, and we are having x k star is equal to a0 plus mu k a1. That we are getting from the series sequence of values. We need 2 equations, 2 unknowns, because a0 and a1 only 2 unknowns here. From here another rule is there for mu k is equal to c into mu k minus 1. For interior method c is lesser than 1, for exterior method c is greater than 1. If we consider these conditions together, 3 conditions together, then we can find out the value of this and this, all right. What we see from here, that if mu, as I said for interior penalty function method, if mu tending to 0, then we are getting the optimal solution. That is why if we just substitute mu is equal to 0, then we will get the true minima, which we were not getting through the process, iterative process. We will see the true minima will be equal to a0. That is the beauty of this method. That is why we can resolve the disadvantage of that interior penalty function method by doing the extrapolation technique, and we can guess the true minima. And another difficulty is there for solving the interior and exterior penalty function method is that the starting point is very important, because in the interior method we are considering the starting point as a feasible point, and for the exterior penalty function method we are considering the starting point as the infeasible point. But from where to start, which value to take as a starting point, that is very important for us. That is why for this case we are considering, we can give you some idea how to consider that starting value with this example. Small example, just you see. If I consider this example, then we will see that we are having the objective functions and 4 constraints. Here we have considered constraints as linear, we can consider constraints as non-linear as well. Now, in this case, if we just draw the graph of it, we will see that the functions will be like this. The feasible space will be, this will be the feasible space, and objective function, this is the contours of circles at centering at 6, 7. That is why circles would be like this. These are the contours of circle. Certainly the minimum will lie here, alright. That is the minimum solution for this. Now, if we apply the exterior penalty function method, then we have to construct the unconstrained problem in this fashion. Just see, minimize f x, that means x 1 minus c square plus x 2 minus 7 square plus mu max of 0 minus 3 x 1 minus 2 x 2 plus 6 square plus mu max of, this is so big one and very difficult to handle, but so easily we can do it. Just to see, that would be 0, 2 by 3 x 1 minus x 2 minus 4 by 3. This is the exterior penalty function method, and this is the function we are considering by augmenting the penalty function. And if this is so, if we apply the technique, then we have to differentiate with respect to x 1 equate to 0, x 2 equate to 0, very difficult to handle this. That is why what we do, we will start from a point, let me consider 6, 7, that is the infeasible point. If we just see the feasible space, here 6, 7 is far away from here, that is why 6, 7 is the infeasible point. That is why very nicely we can consider the point 6, 7. If we just substitute 6, 7 in every constraint, we will see that all constraints will satisfied except this one, alright. That means for all the constraints we are getting the value, here the values are, we can get the values at 0. Actually this square is here outside, not inside, alright. Now, we will get the maximum value as 0, because 6, 7 will be satisfied and that would be the negative value, and here also it will be satisfied, only this one we will get the positive value for 6, 7. That is why if we start from this point, this unconstrained problem will reduce to another unconstrained problem, which is very easy to handle, alright, because all are cancelled because of 0 value. Now, we can consider this as a phi function here. We will consider del phi by del x 1 equal to 0, del phi by del x 2 is equal to 0. That is why, as I said, starting point selection is very important. If we intelligently select the starting point, then it may happen that few constraints will be critically satisfied, few constraints will be satisfied with the less than sign, then we can reduce the size of the unconstrained problem. If we just equate to 0, we will get the value for x 1 star is equal to 6, 1 plus mu divided by 1 plus 2 mu. X 2 star is equal to 7 minus 6 mu divided by 1 plus 2 mu. And if mu tending to 0, then we will get, this is we are considering mu tending to infinity here. If mu tending to infinity here, we will get x 1 star is equal to 3 and x 2 star is equal to 4, alright. That is the solution of the original, optimal solution of the original problem. So nicely, so easily we are getting with the exterior penalty function method. Instead of applying this technique, let us apply the iterative process and let us see what is happening. We are starting from mu value 0.5, we are getting x 1 star as, and we are starting from 6 7, because as I said again and again, for solving the unconstrained problem, few some techniques are there where we need the initial feasible initial solution, initial guess, optimal solution is very important for us. In that case, the selection is very important. If we select this solution nearer to the optimal, the number of iterations will be less. Instead of 6 7, if we consider 60 70, 63 73, anything, then it may happen that we have to do the iterations, more number of iterations here. Now, if consider mu is equal to 0.5, these are the optimal solutions, mu is equal to 1, this is the optimal solution, 4 5, and if mu is tending to infinity, for bigger mu, just you see the value is approaching, x 1 is approaching to 3 and x 2 is approaching to 4, and just now we have got the same solution with the classical technique, alright. That is all about the interior and exterior penalty function method. And the idea is that with this method very nicely we can solve the nonlinear programming problem, and though it is having certain disadvantages, that is the selection is very important, the mu value is very important for us, but the method guides us in such a way that we can reach to the optimal solution of the original problem, and we need not to solve even the unconstrained problem, constrained problem, and we are solving the sequence of unconstrained problem. That is why it is being named as the sequence of unconstrained minimization technique as well. That is all for today. Thank you very much.